Hey, let's take a look here at section 6.5, applications of exponential and logarithmic functions. So in this section, we're going to be using what we did in the last two sections. We're going to use our equation solving prowess now, along with a few little formulas that we're going to talk about. So yeah, the first thing we do is talk about money. So yeah, simple interest. We know what interest is. It's money that we add to whatever we borrow, and we got to pay more back, right? So simple interest. So the amount of interest I accrued at an annual rate of R on an investment P called principal. So we start out with this amount, right? That's the amount of money we start with, and we're going to earn this much as a percentage for each year. So interest here is going to be our principal, whatever we start with, multiplied by the rate, multiplied by the time. So yeah, this is what simple interest is. Now, we don't really want to say much about interest. Usually, we want to make statements about the amount of money that we have altogether in an account. So if we're going to have the total amount in the account, we're going to have whatever we started with plus however much interest we've earned. So our amount is going to be whatever we start with plus the amount of interest that we earn. Now, if we want to write that in a fancier way, we can factor out the p there and have 1 plus r times t. Okay, so if we want the entire amount in the account, there's a nice little formula for us. But really the big deal is that this is simple interest, and we can just add the simple interest to what we started with, right? Okay, so we've got a pretty easy application problem here involving that. So we want the balance of an account that started with a principal of 300 if the account earns 5% simple interest for 4 years. Okay, so the amount is going to be the amount that we start with, right, $300, plus whatever that interest is. So the principal times the rate times the time in years, right? So something to be careful about here is that our annual rate, this is the amount of money it earns every year. So we got to have the units match up. Later on, we're going to have that the time does not need to be in years, but for these examples that involve money, our time is going to be in years. So okay, anyway, we can compute this, right? This is going to be 300 plus. What is this? We can rewrite this in a different way, right? 5 over 100 times 4. So this piece is going to be 15 times 4 would be 60. So we get 360. So we would have $360 if we would have an account with a principal of $300 and we're earning 5% simple interest for 4 years. Okay, so simple interest is, well, just that. It's simple, right? So next we're going to look at compound interest. So there's a nice formula for this. And maybe we can just talk about this just a teeny tiny bit. So if I because the way that investments work or the way that loans work isn't simple interest, right? So every once in a while, we're going to take whatever the total amount is, and we're going to add that interest to the principal, and we're going to compute interest on that amount. So let's just look at this real simply. If I have interest compounded one time, I'm going to have it look like this, right? Well, what if we make that be our new principal? Well, if that's our new principal, then I'm going to compound that again. So my amount is then going to be my principal, what we start with, plus, well, the principal that we started with times the rate times the time, right? So now we see here that we've got a common factor, and we can factor that out, right? P1 plus RT, and then what's left would be 1 plus RT. So we would have our principal, whatever that is, and then 1 plus RT squared, right? So maybe it's not too big of a stretch of our imagination to say, well, if I compounded that 3 times, that number right there would probably turn to a 3, right? Well, finding the the nice formula for this is a little bit more complicated because we're not just going to compound once a year, which is what we were doing up here, or twice a year, which is what we did up there exactly, right? Because that was a 2. We're going to be compounding n times per year. But, you know, it's going to look sort of like this. And mostly the idea here that I was trying to illustrate here is, boy, isn't this reasonable? Like it should look kind of like this, right? Because if I did simple interest and I compounded it twice, it looks like that. Well, wouldn't it be reasonable if I compounded it more than once a year, that we would have something like this? Well, the bottom line is we've got a nice little formula here, and we can identify the variables, and we just kind of plug them in. Okay, so the difficulty with these problems usually is figuring out what n is. So maybe we can write down a few keywords here. So if I have, I don't know, daily, n is going to be however many days there are in a year, right? 365. If we do monthly, we're going to use n equal 12, right? There's 12 months in a year. If we do quarterly, then we're going to use n equal 4, right? Quarterly means 4 times a year, and so on, right? We can do more than that, but that's kind of the basic idea. Okay, so we've got another problem here. Suppose $300 is invested in an account which offers 5% interest compounded monthly. Something that is going to be, let's do number 1, something that's going to be good for you strategy-wise is to just look for the keywords that are going to tell you which nice formula to use. So if we see compounded monthly or compounded at any regular interval, we're going to say, okay, well, I'm using my compound interest formula. So we would use this nice formula here. And our compounded monthly, that's what's going to indicate that we're going to use that nice little formula. Okay, so really we just need to identify what the values of these variables are, right? So A, P, R, N, and T. And then we're just going to plug them in there and find the missing thing. So for part 1, how much is in the account after 4 years? That's the number that we want to know. We don't know what that number is. That's what we're looking for. P, this is the amount we start with, so that's $300. R is our interest rate, looks like 5%. A common error here is to just put a 5, but be careful there because 5%, this is 0.05, right? So be careful with these because you're going to be tempted to just put 5 in there. Okay, N, compounded monthly, there's 12 months in a year, so we're going to use N equal 12. And then T is the amount of time, so this is going to be 4 years here. Okay, well now that we have all of this, we just plop it on into this nice little formula here. So we've got A at 4 years is the principal, what we start with, and then we have 1 plus then our rate over the number of compoundings raised to the 12 times 4 power here. So right, we can find that amount and we can maybe crank that on. Okay, so here's where we're going to probably have a bit of an issue. So we can't use calculators on our quizzes and on our exams. I guess we don't have quizzes regarding this. So yeah, the problem is here we can't use a calculator. So in your homework, it's going to have you type that in. And it's going to say round it to this many decimal places. And you know, we can do that. We can type that into a calculator and we can get a value. And yeah, we can plug that into a calculator. We'll get that's 366.27 if we're rounding to 2 decimal places. And this would make sense to give our answer in terms of dollars, right, rather than in terms of some, you know, expression involving exponents. But for purposes of your exam, we're not going to be able to just compute this all that easily. Whoops. What did I do? Okay, we're back here. So, yeah, we're not going to be able to compute that very easily, if really at all, using pen and paper. So this right here, this is exactly what we would want in an exam sort of situation. We want to just leave it just like this and don't mess with it. As soon as we get the desired result here, then we're done and we can say, okay, this is the answer. But in the situation with your homework, it's going to want you to type this in there and round it. So yeah, we can use the calculator on our homework, and we should, but on the exam, when it asks for this, we're not going to be able to plop out that decimal because we're not going to have a calculator. So just leave it blank and write this in your scratch work, and I'll give you credit for this, provided, of course, provided that we have the right expression there. So yeah, this is what we're looking for an exam, and for our homework, we're going to type in the calculator value. Okay, let's keep going here. So 2, write a function that gives the amount in the account after t years. Well, we just have, this is part 1, we have an expression after 4 years. Well, why don't we just put a t there, right? So put a t instead of your 4. We got 300, 1 plus 0.05 over 12 to the 12 times t power. And there we go. That's it. Yeah, we just substituted a t instead of that 4 because we don't know what year it is. Okay, now we want to write number 3. How long will it take for the initial investment to double? Okay, well, isn't this kind of the same problem as number 1? Except for we don't know t. But if I doubled my amount would be 2 times 300, so that's 600, right? Okay, so now we can take all of these and plop it into our nice little formula, right? So our amount is 600, and then we have our principal, 1 plus our rate over the number of compoundings times the number of compoundings times the time it takes. So now we can take this guy and solve for t. Okay, we can do that, right? We have these strategies from the last couple of sections. We want to get all the exponential stuff alone. So we're going to divide both sides by this 300 there. We got 2, right? 600 divided by 300, that's 2. 1 plus 0.05 over 12 to the 12t power. Okay, now we've got our exponential expression isolated. It's alone. So now we do the usual thing, right? We're going to take natural log of both sides. And that makes it so we can rewrite the exponent in a factor position. So the left-hand side just stays the same. And then the right-hand side, we can write that exponent down in a factor position. So as a product, right? Okay, and now all we have to do is divide. So t is the left-hand side divided by 12 divided by this. So we got 12 natural log 1 plus 0.05 over 12. And yeah, in an exam sort of situation, that is the expression that we're looking for, and this is completely fine. Now in your homework, it is going to want you to round this, so we've got to round it, and we can do that. Punch it into a calculator, we get 13.89 years if we rounded that to 2 decimal places. Okay, good. We did it. So yeah, again, this is what we want on your scratch paper on your exam. We want to write the exact expression right there. But your homework is going to ask you for that. And in the homework situation, yeah, punch it into a calculator, that's fine. But on our exams, we don't have a calculator, so I'd probably just leave that blank. And I'll give you the credit on the back end there. Okay, so we can do, looks like the same problem again, right? So how long will it take an investment to triple if the interest rate is 7.2% compounded daily? Okay, well let's approach this in the same way. We got an A, a P, a rate, time, number of compoundings. Okay, so our amount, well, what are we going to put here? We don't have a principal, right? They didn't give us a principal, so we don't know what that is. It's just some number. But if we knew what it was, to triple it, we would have 3P, right? Okay, and then our rate, we've got our rate 0.72. Our time, this is what we're looking for, so we don't know what that is. And N, we're we're compounding daily, so it's 365 days in a year. Okay, so now we can take this and plug it into that nice formula there. So we've got our amount is equal to the principal times 1 plus our rate over the number of compoundings raised to the n number of compoundings times t. Okay, great. And now we're still going to do the same thing here. We want to isolate the exponential part, so we can just divide both sides by p. And if we do that, well, they just cancel out, right? So we got 1 plus 0.072 over 365 raised to the 365t power. And now we just do the usual stuff, right? So we've got an exponential expression isolated. We're going to do the natural log of both sides. And then our exponent gets shifted down to a factor position using that nice product rule. Then we've got natural log of 1 plus 0.072 over 365. And now we're home free. So we got t is the left-hand side divided by the factors on the right that we don't want. And now, as far as an exam answer, this is just fine. This is exactly what we want. But now in your homework, it is going to want a decimal, so we should crank that on through 15.26 years. And we can, use a calculator there and find that value. Okay, cool. So now we can find, how long will it take an investment to triple? We could find how long it takes an investment to quadruple, or give us 5 times what we had, or something like that. All right, great. All right, how much money do we need to invest now? So this is principal, right? So amount, principal, rate, time, number of compoundings. All right, so we're just approaching this the same way we've done these others. How much money do we need to invest now? That's the principal, we don't know. Our rate is 0.053. Compounded quarterly, so quarterly, that's 4 times a year, quarterly. We want to have $5,000 in our account, so that's the total amount after 25 years. And now we're, off to the races here. So we just plug all these values into our nice equation, and we can solve for what we don't have. So we got 5,000 is our amount. That's got to be equal to the principal times 1 plus 0.053 over n raised to the n times t power. And really all we have to do is divide, right? So p is 5,000 divided by that exponential expression. Might as well write 100 there, right? 4 times 25 is 100. So at this point, this would be fine. Just leaving it just like this would be fine for our exam. But as far as your homework goes, it's going to want you to crank that through a calculator. So we get $1,340.63. All right, great. All right. Continuous compound interest. So yeah, the big formulas that we need are the one we're using here. So for compound interest, but then we have continuously compound interest is slightly different, and we might breathe a sigh of relief because this one is easier. So saying where this comes from might not be too easy to do at this point because we don't know exactly what a limit is. It all has to do with this number E. The way we define this number E is a number that's it's a limit. Let me just write it here real quick. So this is what the number E is. When we say limit as n goes to an infinity, it's the value of this expression as this n gets larger and larger and larger and larger. So if we pick something like n equal 1,000,000, and I put that into here, so 1 plus 1 over 1,000,000, raised to the 1 million power. That's 3. This is approximately E, right? So put in numbers bigger and bigger and bigger and bigger and bigger. So the point of this, I guess, is to say, hey, isn't it reasonable that we would have something that looks like this? Now, thinking about our compound interest formula, don't these things look similar, right? Those things look pretty darn similar. And if I think about continuous compound interest, I want to continually compound. So I'm compounding all the time at every moment of every day. So how many compoundings per year is that? Well, wouldn't that be infinitely many? So, you know, super hand wavy explanation for this, but hey, isn't it reasonable? So our amount, if we compound continuously, is going to look like this. So I don't know. The two big formulas that we need to know from this section are these two, right? And this is compounded n times per year. This is continuous compounding. So they're really similar formulas here, with the big difference being that we have E in one of them, right? Okay, we're going to use the continuous compounding one in a couple of different contexts, but the first one is going to be money. So how much money is in an account that started with $1,000 and earned 5.34% interest compounded continuously for 3 years? So yeah, when we're doing these problems, we want to be looking for these keywords, right? Compounded continuously. So if it's compounded continuously, immediately we say, all right, I've got this nice formula, and I'm going to plug in what I have and then solve for what we're missing, right? So A is, we don't know. P is how much we started with. Interest rate is 0.0534, and our time here is 3 years. Okay, so we're just going to, A of 3, this is our principal, times E to the R times T, and that's it. Now we're just going to crank that on through our calculator. We get $1173.75. And again, for an exam situation, that's what we want right here. And this is perfect to put just right in your scratch work. Right there it is. But again, for the homework, it's going to want you to round that to 2 places. Okay, great. So yeah, all these are kind of starting to look the same, I hope. We're just identifying what do we have and then solving for what we don't have, right? Okay, what was the continuous compound interest rate? So we don't know what rate is, but our keywords, we got continuous compound, right? So we've got A is P-E-R-T. Okay, so we identify these things. We invested $300 in an account 4 years ago, and now it's worth $500. So the amount now is $500. The principal that we started with was $300. The rate was, that's what we want, and then time, that was 4 years. So after 4 years, we had $500 in our account that started with $300, and we were earning an unknown rate. So we'll just leave that R in that position. Okay, so now now that we have this, we're at the point where we're just going to use our equation solving strategies from the previous sections, right? We want to get that exponential expression alone. So divide both sides by 300. We'll get 5 over 3. And now we've got our exponential expression is isolated on that one side, so we'll just take natural log of both sides. And we're essentially home free here, right? So now our 4R becomes a factor. Or we could think about this using that the inverse properties of these functions, right? We had log base b to the x is equal to x, isn't it? Well, that's log base e of e to some power. Well, it's just that power. Okay, so we've got r now. We'll just divide both sides by 4. And we're done. So again, for exam purposes, that's what we want. But for your homework, it's going to ask you to plug it into the calculator, so we can do that, right? 12.77%. But getting here is the point, and this is what you're going to be having on your exam. Okay, good. Now for other applications. So uninhibited growth and radioactive decay, both of these have the same formula. They might not look the same, but they're the same, right? So both of these things, n sub 0, this is the initial population, so that's the amount we start with. So think, wow, that doesn't look very good at all. So think of principal. Principal. So it's just like those investments where we had continuous compounding, but we're just using different symbols here. Okay, so we're going to have both growth and decay. So with growth, we're going to be increasing, and with decay, we're going to be decreasing our amount. Okay, so let's check out this first example. An initial population of 12 cells grows to 5,000 cells in 1 week. Wow, that's fast. That's really fast. Assuming that the cells follow the law of uninhibited growth, find the number of cells present after 10 days. Well, shoot, if it grew from 12 to 5,000 in 7 days, it's going to be a lot after 10 days, right? Because that's, wow, exponential growth is pretty fast. Okay, so let's just kind of take this just like the other ones, right? So we have law of uninhibited growth. So that means we know that it's going to look like this. That's super bad. So n of t is n sub 0 e to the kt power. So now we're just doing the same thing, right? So n, this is question mark. That's what we want, right? N sub 0, this is the amount we started with, so that's 12. Our k value, well, we don't know that either, do we? And then our time, we want 10 days, right? So the difficulty with these problems is going to be finding this k value. And this works out just like it did when we were talking about other structures. So, for example, if I have a parabola and I give you a point on the parabola and I gave you the vertex, we could just plug that stuff into the known formula and just solve for the missing stuff. Well, this is the same thing here, right? An initial population of 12 cells grows to 5,000 cells in 1 week. Well, that means that the amount after 7 days would be the number I started with times e to the k times 7, right? So we're just plugging in the stuff that we know and solving for what we don't know, right? N of 7, so that's going to grow to 5,000, isn't it? Okay, so now I can take this guy and solve for k. And we can do that in the same way that we've done these other ones. So what? First we divide by 12. So e to the 7k, we can rearrange that too, is 5,000 divided by 12. And if we want to, we can simplify that. And we probably should 1250 over 3, right? If I divide both those by 4, right, we get 1250 over 3. Okay, now we can do our natural log business. So we have these two things are equal. So I've got natural log of e to the 7k would have to be equal to the natural log of the right-hand side. All right. So then we can solve for k, right? Natural log of e to some power is just going to be that power. And maybe we can come up here and say k is equal to the natural log of 1250 over 3 divided by 7. Okay, so now we have k, and we can maybe put it out in our little chart here. So we got natural log of 1250 over 3 over 7. Okay, so our little formula here becomes n of t equal what we start with times e times the number k, so that's natural log 1250 over 3 over 7 times t. And now we can find what it is after 10 days. We just put in 10. So n of 10 equals 12 times e, and then our exponent, natural log 1250 over 3 over 7 times 10. So in our exam, if we're asking a question such as this is exactly what we want to have in our scratch work. But again, in our homework, it's going to want us to plop this on into a calculator, so we can do that as well. So I got 66,334 approximately cells. And it's going to tell you where to round. It'll say, round the nearest whole number or something like that. So there we go. We can do it. Okay, so yeah, the difficult part in this one and the difficult part, what's going to be in the next problem, is finding this k value. So again, here's what we did. We have a nice formula that we know that it has to look like, and then we just plugged in all of our stuff that we had, that we were given, and we only have one missing value, and we can solve for that. So think about what we did when we had parabolas, and we said, hey, find the standard form of a parabola with vertex such and such, and goes through this point. Put in the stuff we know, solve for what we don't. Okay, great. So that was uninhibited growth. Now we're going to have decay. So radioactive decay. So really, this is the same problem, just phrased in a slightly different way, right? We're going to do the same stuff, but this is going to give us trouble. So half-life, this is the amount of time to, or for, half of the substance to decay. So for this one in particular, if I started out with, if I start out with 5 grams of the element now, in 8 days, I'm only going to have half of that. So in 8 days, I'm going to have 2.5 grams. And maybe we can write that, because that's what we're going to use to find this k value, using the nice little, using the nice formula from above. We can say that to find k, we're going to say a of 8 days is half of what we started with, so 5 over 2. And, we could write 2.5 if we really want to, that's fine, but, 5 over 2 is fine too. Okay, so A is this, the amount we start with is 5, the rate, which is K, we don't know what that is, that's what we're trying to find, and T is 8 days. So we can plug all this stuff into our nice little formula here. We've got A of 8 is 5 halves. That's going to have to be what we started with times e to the kt power. So that's going to be 8 times k, whatever that is. Okay, so we're going to do the same things we've been doing. We want to find that k value, so we're going to solve for k. We want to get the exponential expression alone first. So what? We're going to divide both sides by 5. Okay, and then we do what we usually do. We'll take the natural log of both sides, and now we have that the natural log of 1/2 is equal to 8k, so that tells us that k has to be natural log of 1/2 divided by 8. And now we're home free, right? Because now we can take this k value and put it into our nice function. We know that our function has to look like this, right? A of t has to be the amount we start with, times e raised to the k, which is natural log 1/2 over 8 times t power. So if we want to know how much is left after 30 days, we're just going to plug in 30. So we got a of 30 is 5 times e to the natural log 1/2 over 8 times 30. And again, for our exam purposes, That's exactly what we want. We don't have to simplify this anymore. This is just perfectly fine. But for your exam, or excuse me, for your homework, it's going to want you to plug in those numbers to your calculator, and we can round to whatever value that they want you to round to. Okay, so good. The difficult part, again, I think is finding this k value, and that sort of stems, the trouble there kind of stems from what the heck is it that we're even doing. But the bottom line is we have a known form of an object. I know that it must look like this, and I have a specific instance of the object. I know that this stuff must be true. Well, plug it in there, find the missing thing, right? And that's exactly what we did right here. Okay, good. So that's it for this section. Whole lot of applying what we learned in the last two sections, right? We're essentially just solving exponential equations using our logarithm tricks. Okay, good. So that's again, that's it for this section. So thanks for watching the video. Have a great rest of your day.